Over the years, many students came to me asking how one become an applied mathematician today and what is really applied mathematics. So I decided to present in a few slides what I think is an applied mathematician, and specifically how somebody can become an applied mathematician. So I think master student, undergrad student should benefit from this overview. So let's ask a few questions. First of all, I would like to discuss here what I think is an applied mathematician. Second, how to become an applied mathematician through studies at a graduate level and undergrad level. And specifically, I would like to discuss the recent direction of modeling and computational biology, which I think has really renewed the notion of what is an applied mathematician. And finally, we can ask how to recognize that somebody is doing or not applied mathematics. And I would like to say that applied mathematics is very close to what we can call today applied theoretical physics or statistical physics, because in physics usually people learn learn how to model a process, a biological process, that is how to go from the features of the biology to the equations that are usually needed to simulate or to analyze the system. So what is an applied mathematician? As we just discussed now, really applied mathematics is very close to this subject of theoretical physics. But basically, this is somebody that is using and is developing analytical theory, that is equations, mathematical equations, and computational approaches which are either analytical, that is how to derive the solution of equation, which is usually very hard and almost impossible. So asymptotic analysis is usually used to explore what happened when, for example, there is one or several small parameters in the problem. But most important, developing computational approach means develop simulations and rational simulations that are derived, that are under control, in order to approximate or to explore the parameter space of the problem. For example, what happens when several parameters do vary, and hoping that the simulation provide a good sampling of this space. And usually this is very hard, because if there are some bottlenecks, that is, if there are some computational property that makes the simulation very long, then usually people have to wait days, months, or years before getting results. So this is usually unacceptable to wait so long. So numerical methods have to be developed in order to solve these questions, and coarse-grained model are usually necessary, that is, not to model the entire system, but to model a piece of it. And this is very important in biophysics, in biological science, in physics, in chemistry, where usually are the most interesting problem, as well as, of course, engineering. So there are very big list of historical examples where applied mathematics has been fundamental and very useful. For example, we can have in mind the Fourier synthesis, when you write a function in Fourier series, so that we can represent sounds at different frequency. And all of this analysis, which is really hundreds of years old, is even seen today, and has found new applications, such as in speech recognitions or baby cries interpretations. And this is based really on how to decompose a function, how to write a functions with a basis, and sometimes what is very important is to have a few elements on the basis where the function can be represented. There are of course many beautiful examples in inverse problem in medicine that are important for reconstructing a signal after any kind of imaging, such as brain imaging or ultrasound, how you reconstruct the image from the wave. And this is a very important field of work, especially when now there are surgery, or people can burn tissue with a given precision, which is usually not enough, but to burn a specific tissue by, for example, reversing waves. So again, this is a very active part of applied mathematics. Another direction is, of course, how to build computer, to crack code and to make codes. And the best example, I think, in history were John von Neumann and Alan Turing. And to continue with Alan Turing, I would say that this is also a beautiful example of how applied mathematics can be used to understand biological process, referring to his 1952 papers about morphogenes and predicting that molecule can go from one cell to another to spread some signal. And of course the question is how the tissue can interpret these morphogenes in order to elaborate itself. So it's clear that over the years, over the centuries, mathematics has been very powerful in designing new tools, and not only tools but also concepts that have invaded many fields of science. Now, how to become an applied mathematician. So this is more focused and dedicated to undergrad students, master students, and even PhD students. So what really needs to be studied if you want to do something that has an application, and if you start, you don't know what will be the application, so you better be equipped. So for this, I think the best is, of course, to have general knowledge about partial differential equation, dynamical system, stochastic processes, and of course differential and even Riemannian geometry is important to reconstruct, for example, data from waves or from signals. And of course numerical analysis is quite important to understand how to solve equations, how to compute integrals, and to do any type of simulations. So this is for the mathematical part. And of course you cannot do anything relevant if you do not know the field that you are going to be working into. So physics is also very important. Statistical physics, polymer physics, electricity, mechanics, semiconductors. I mean, all of the classical physics in quantum mechanics, all of this physics is fundamental to know at least the basis. Of course, chemistry and biophysics at different levels. And of course, biology can also be learned, although it is not necessary as the background. But if somebody wants to go into applied math in biology, molecular, cellular to population biology are very relevant. And finally, it's important to have knowledge in engineering, especially in signal processing, how to denoise, how to deconvolve the signal, how to get rid of the noise, and this is very important in communication theory. And finally, it's not enough to get the theoretical knowledge. It's very important to spend time in the field of interest where people are going to teach you what are the questions. And usually they are the people that are doing the experiments. So now the next question is, where are the good program and the good PhD program? So I would say that they are spread all over the world. Of course, there is a very nice tradition in United Kingdom which has been brought to New Zealand and Australia. I would say they have the best program are certainly in the United States, and here they are spread between the East, the West, and the Midwest, and you have excellent school. I would say this is a bit different in continental Europe, where usually this type of approach is made in the physics department. And I would say that the applied math often means in continental Europe numerical analysis or theoretical work to prove convergence of algorithm, which is only a small fraction of what is applied math. But it's still very important to have this knowledge, although this is only, again, a very small fraction. So finally, let's discuss a bit more about modeling and analysis in computational biology. So this is really a new field of, let's say, 10 years that requires not only to have a good knowledge in applied math, but a serious background in the other fields like biology and biophysics. But I would say first, the best way to go in this direction is to first to get trained as an applied mathematician or a theoretical physicist or a chemist, and then learn the necessary biology to go into the field of interest. So, and now how do you recognize somebody that is doing work in applied mathematics or applied theoretical physics? I would say the first thing is in publications. Somebody that can publish in various fields of science as a leading author, to for example, develop methods in mathematics to resolve equation, let's say, for example, asymptotic analysis. But also, we should demonstrate that the person has result in the field of application. And what is the meaning of this? It means to publish as a leading author in applied journal, such as the journal in the community of the application. So for example, not only as an applied mathematician, people should publish in the classical SciAm type review or Journal of Statistical Physics or the physics review type journals or Journal of Physics. There is plenty of them. But in addition, if somebody is interested, for example, in application to biology, then it is important to show achievements of concepts or method of calculation for the community. For example, in biophysics, just biophysical journal or the PLOS type journal, or if it is in engineering, in EEEs, or the engineering literature. So I think without this dual type of publication, it's very hard to show that somebody can do can apply mathematics to a subject, because the recognition from the community is usually going through this dual type of publication, not only produce mathematics in terms of analysis or simulations, but also show that this simulation can predict features or can allow to reveal features in data, because the mathematical analysis of the statistics allow to interpret data. So to conclude, I would say that we are in a challenging time where quantification and the possibility to calculate something is really needed at various scale. For example, in biology, from the molecular scale, going to the cellular, and then to the population level. So being able to compute and compute correctly, which also implied that to do modelings are really needed in various directions of, in various fields of science. And the experience that we have seen here in our lab is that there is no problem after to find a job either in the academia, in industry, or simply to create your own job by finding a new methods, like in coding or like in interpreting and understanding the stock market, or now in biology. So I wish everybody that wants to go in this direction and become applied mathematician, a very good luck.